So a topic that was in the environmental chemistry option and has been spread out into a number of the different core topics is what's going on with the molecule ozone, and specifically what's going on with ozone in what we call the ozone layer. So as a brief intro, this image gives you a sense of the Earth and then the various layers of the Earth's atmosphere. Now the ozone layer is an area towards the top of what we call the stratosphere in our atmosphere, and it's not like when you go up there you would see it. The ozone layer is just a part of the atmosphere that has a relatively high concentration of ozone. As a reminder, ozone is O3, which is it's a type of oxygen. So it's an allotrope of oxygen, and its molecular formula is O3. So if we walk through how this happens, at the top of the stratosphere, really the very top of the stratosphere, regular oxygen, so O2, gets hit by ultraviolet light that we call UVC light. So ultraviolet light can be broken down into UVA, B, and C ranges, with C being the shortest wavelength, highest energy type of that UV light. So as UV light comes in from outer space, from the sun, and is traveling towards us, it starts to collide with molecules. And so pretty much all of the UVC light gets taken out of existence, really, by oxygen molecules before it ever gets to Earth, which is a good thing, because UVC light, again, is the highest energy kind of UV light. It would cause a lot of damage to us and other living things if it made it all the way through the atmosphere. So that UVC light hits oxygen molecules that are sort of up at this range. I can try to draw straight. So right at the top of the stratosphere. That's really not very straight. Sorry about that. So along that squiggly green line is essentially where UVC light is coming in, hitting oxygen molecules and splitting them apart into monatomic oxygen. Now, you have to understand that up at this level of the atmosphere, the concentration of gas particles is so low that actually a number of these oxygen atoms stay as oxygen atoms. They don't actually collide with anything else for a good while. So basically up at that level, you are making a lot of single atoms of oxygen. And as those oxygens naturally sort of diffuse down lower in the atmosphere, they start to collide with oxygen. As the further down you go towards Earth, the more and more gas there is, so the more and more oxygen there is. So further down, the oxygen atoms start colliding with oxygen molecules, and that's how all the ozone gets formed. So it only forms here because up at this level is where you're making a lot of monatomic oxygen. We add in a little writing. So up here, you've got monatomic oxygen being formed. And below it, down here, you've got diatomic O2 in higher concentrations. And so right where those two things meet, at the red, is where you're going to end up with ozone formation / high concentration, and that's O3. So that's how it gets formed. UV light plays a really instrumental role in that, because the really powerful high energy UV light is breaking apart the oxygen up here, and that's allowing us to have the monatomic oxygen, which then combines with the O2 to make the ozone. Okay. As a side note, this reaction is exothermic when we form ozone, and actually the relatively high temperature of the stratosphere, this region of the atmosphere, the reason why it's its own section of the atmosphere is because it has sort of a strangely high temperature. Normally, as you go further and further away from Earth, it gets colder and colder. And it does so for a while, but then there's this part of the stratosphere where it actually gets warm again. And the main reason why it's getting warm is because of this reaction that's taking place and releasing heat into the surroundings. So the ozone layer is just part of the atmosphere that has a relatively high concentration of ozone. It's still only around 10 parts per million. So it's out of every million grams of air that are up there, only one gram of it is ozone. So it's still a very low concentration. But ozone absorbs a different kind of UV light. It absorbs stuff that's in the UVC and UVB range. So things with 20 to 320 nanometers of wavelength. So the minimum or the longest wavelength that light can have to split apart ozone is 320 nanometers. And so that represents a certain energy of light that's able to break apart ozone. So the breakdown process is that ozone gets hit with this UV light somewhere in that range, and it splits back into oxygen and into monatomic oxygen, so O2 and O. And then because where the ozone layer is, there's lots of oxygen around, usually that monatomic oxygen just collides with the O2 and reproduces the ozone. It can also react with other O's and make O2, or it can even react with other ozones and make two O2s. But mostly we think of it as this is the breakdown process, and then essentially the reverse reaction happens and it reforms ozone. So there's more or less an equilibrium of ozone in that ozone layer where you have ozone being split into these things, but then you've got essentially the reverse reaction taking place as well. And so the ozone is replaced and equilibrium concentration is established. So ozone is constantly being formed and being broken down, but in that region, you essentially get a steady concentration of ozone as it's broken down and then reformed. Okay. Now, in order to form ozone, we have to break apart O2, and O2 gets broken down by light that has this wavelength or shorter. So as wavelength gets shorter, so as wavelength decreases, we should know that frequency of that light increases, and that also means that the energy of that light increases. So this is the longest wavelength that will break apart O2. So in this part, we're talking about oxygen. This is the lowest energy light that can break apart oxygen. So if you rework your equations, and you had to do this on the final exam before, I don't have my symbol for lambda, so I'm just going to write lambda, which is the symbol for wavelength, and then V, which is the symbol used in the data booklet for frequency. So the speed of light equals wavelength times frequency. The other equation is that the energy of light equals Planck's constant times frequency. So if I know the wavelength and I want to solve for frequency, I can do this. I can say that C divided by lambda, or my wavelength, equals frequency. So I could then, in this equation, plug in C divided by lambda. Okay? And so if I plug these things in, I'm going to get an energy value out. It's going to be an energy in joules, and it's going to be the energy required essentially to break one bond, one O to O bond. So it'll be a very, very tiny energy. If you want to know what it is per mole, you have to times this energy by Avogadro's number times 6.022 times 10 to the 23rd, and that will give you the energy in joules per mole. How much energy does it take to break a mole of these bonds? And then if we want to get really crazy, we could convert it to kilojoules by dividing it by 1,000. And what you actually find is that when you plug in the numbers, so if you look in table 2 and you get the value for Planck's constant, and you look in table 2 and you get the value for C, for the speed of light, and we plug in 240 times 10 to the minus 9 meters for our 240 nanometers. So we plug in those constants and we divide by this wavelength. We'll get an energy out. If we multiply it by Avogadro's number, we'll get an energy value, and the energy value is actually equal to the bond enthalpy for O2. So it's further backing up the value of the bond enthalpy, that the bond enthalpy for the O to O double bond, which is listed in table 11, if I look it up right now, is 498 kilojoules per mole. If you do the calculations, and we can double check it in class, if you do the calculations for this wavelength of light and multiply it by Avogadro's number, you also get 498 kilojoules per mole. So the energy of light needed at a minimum has to have 498 kilojoules per mole, or else it won't break the O2 apart. You could walk through the exact same calculations using 320 nanometers, which is the shortest or the longest kind of light that can break apart ozone. Notice it's a longer wavelength, so it's less energy. And that makes sense because the O to O bond in ozone is a 1.5 bond order. It's a resonance thing, and the bonds are actually about 1.5. So it makes sense that a longer wavelength of light breaks this bond, because that's a lower energy light. So it takes less energy to break the bond in ozone than it does in O2. And the type of light that breaks it has the same energy as the bond enthalpy for those molecules. Okay, that's more of a review topic. This is looking again at the ozone formation and destruction. So natural ozone formation involves these two steps, O2 breaking into 2 oxygen atoms, and then the oxygen atoms combining with O2 molecules to make ozone. And so net, if you cancel out the monatomic oxygen, which is the intermediate, you end up getting a net overall reaction of 3 oxygens makes 2 ozones. So that's what is taking place up there in the top of the stratosphere. The natural process of ozone destruction is essentially the reverse, that those ozones split apart with UV light, and you can reform some oxygens. Eventually, the oxygens can turn back into monatomics. And so overall, you're making, I think I've messed this up here. So if we don't think about the equilibrium, if we just think about the destruction, we'd have to take that one out. And you have your ozones forming, getting split, and then the monatomics combining to form O2. And it would be the reverse of the original. Oh, I skipped, that's why. I apologize, folks. I skipped past my own part here. So here is the part where we looked at ozone destruction. Let me try to click on it. There we go. Clunky. Ozone gets broken down. The O's can combine and form O2. And if we make this a 2, we make this a 2, and we make this a 2, then the net result is that when ozone gets broken down, 2 ozones ends up forming 3 O2 molecules, and the intermediate of the monatomic oxygens eventually cancels. Overall, where is it? There. Okay. Overall, I put both those things together to show that there's an equilibrium. Ozone getting split, forming oxygen, but oxygen also getting split and resulting in ozone. And so net, the amounts of everything don't really change much in the ozone layer. Okay? That is until you add a catalyst. Okay? So the hole in the ozone layer is really, it's not exactly a hole, it's just an area around in the atmosphere where we get really low concentrations of ozone. It tends to happen mostly over the poles, especially the Antarctic, and it allows a lot more UVB light through down to Earth's surface, which can lead to more sunburn and skin cancer, and eventually affecting immune systems. There is a lower ozone concentration everywhere in the world seasonally, but it's especially bad at the poles. Way beyond the syllabus, but it's actually has to do with how the poles get completely dark and ridiculously cold during their winters, which leads to a whole chain reaction of changes that throws off the equilibrium. And so when first light returns in spring, the light starts causing the creation of some catalysts, which end up breaking down the ozone, and it doesn't get replaced right away until everything warms back up in the late spring and replaces the ozone. So the ozone hole actually takes place in the spring for each hemisphere for that pole, which is pretty cool. Okay, so where does the hole in the ozone layer comes? It comes from, well, from humans, of course, and it comes from things that we call CFCs. CFCs are chlorofluorocarbons. So they're molecules, they're organic molecules that are made of carbon, and then they have some combination of fluorine and chlorine on them, hence the term chlorofluorocarbons. Right? These things, for a long time, were used as refrigerants. So they were used in air conditioners and refrigerators, and also as propellants or aerosols. They are largely very stable. They are largely unreactive. So when they go, if they leak out of your air conditioner or they leak out of an aerosol can, they don't naturally react with much that's around in our atmosphere. So we'd say they have no sink in the atmosphere, nothing that removes them. So they basically get out and they float up in the atmosphere, contributing to global warming, doing all sorts of things, until they get high enough in the stratosphere that there is a kind of UV light that can break them apart. Now, the UV light that they get to, it breaks the carbon to chlorine bond, not the carbon to fluorine bond. That's because the carbon to chlorine bond is a lot weaker than the carbon to fluorine bond. Chlorine is a bigger atom, so there's a weaker nuclear attraction for the shared electron pair. So I should say weaker, I meant to say electrostatic attraction. The covalent bond is an electrostatic attraction between the nuclei and the shared electron pair. It's weaker in the carbon to chlorine bond. So this picture sums it up pretty well, that these CFC molecules, they go up into the atmosphere, and the UV light splits off one of the chlorine atoms. Now, this chlorine atom is called a free radical. It has an unpaired electron. So chlorine, we know, has 7 valence electrons on its own. That's why it rarely exists as free chlorine atoms. But temporarily, it can exist as free chlorine atoms when it gets split by this UV light. And so this is happening in the area where there's a lot of ozone. So these free chlorine atoms, these free radicals, end up knocking into ozone molecules, ripping off oxygen from them, leaving behind oxygen gas, and forming this chlorine-oxygen intermediate. That chlorine-oxygen intermediate is itself a radical, and it can combine then with free oxygen atoms to produce oxygen molecules once again, and reproduce the chlorine. So if you're seeing what happens, we start with a chlorine, and then we reproduce a chlorine. And so it's involved in the mechanism, but overall its concentration doesn't really change. And that free chlorine can then go back and continue to break down ozone. The chlorine is acting as a catalyst. Anytime in our reaction mechanisms we have something that begins as a reactant, gets used, and then gets reformed, that's a catalyst. The difference being the ClO is what we would call an intermediate, that it gets formed and then it gets used, and so net, it doesn't show up in the equation, but we don't have it really initially. Okay, so these chlorine radicals, the net takeaway is that chlorine-free radicals are the catalyst for the breakdown of ozone. And so they speed up the breakdown of ozone, and you can have thousands and thousands of ozone molecules being broken down for every one chlorine radical that exists. Okay. So the mechanism, if we rewrite it in chemical equations, is the chlorine atom, that's the free radical. Sometimes they're written with a dot to show that it's a free radical. Reacts with ozone and makes a ClO free radical and oxygen. And then the ClO radical reacts with an oxygen to make another Cl radical and O2 gas. So net, all you're doing is taking an ozone and you're forming, well, an ozone plus a monatomic oxygen from somewhere. And in the end, you're forming 2 O2s. So it's not that the breakdown of ozone produces something that's particularly toxic or anything. It's producing oxygen gas. The problem is it lowers the ozone concentration significantly, and that means more of that UV light can get through. Okay? So the catalyst is the chlorine radical. The intermediate is the ClO radical. And each chlorine atom can catalytically destroy tens of thousands of ozone molecules. Okay, so this is the summary of what you really need to know about ozone for the IB exam, since I kind of went a bit off on tangents here. The stuff that we covered previously relates to the energy of light. That the type of light that breaks ozone and that breaks oxygen is different, and the energy that breaks down oxygen is of a higher energy and therefore a shorter wavelength. And you can relate the bond enthalpy perfectly matches the type of a light that will break down ozone and oxygen. More specific to the kinetics topic, are these mechanisms. So the reaction mechanism for ozone formation and for ozone destruction, and therefore overall for equilibrium. So this first one shows ozone destruction. So it shows you're starting with ozones, you're forming oxygen gases. This one shows oxygen eventually turning into ozone. This is ozone formation, and together they keep ozone concentration relatively stable most of the time. So those are two mechanisms that you would want to be able to produce on the IB exam. Another thing you're supposed to know is the role of chlorofluorocarbons in ozone destruction. You need to know that they are relatively unreactive. So their relative reactivity is that they're very stable. The carbon to chlorine bond is relatively weak, and so it's the bond that breaks, not the carbon to fluorine bond. And that results in very reactive chlorine and chlorine radicals, which then lead to ClO radicals, and those are what catalyze the breakdown of ozone. The overall mechanism, as I've seen on a mark scheme, is that here's how ozone gets destroyed by CFCs. You have a CFC like this, CCl2F2, which is the formula of Freon, probably the most commonly used one back in the 70s and 80s. It breaks apart, releasing a chlorine radical. The chlorine radical breaks down ozone, and then the ClO radical can react with O's to create O2. Just to point out, the ClO can also itself react with ozone, producing oxygen, and again, reproducing the chlorine radical. So no matter what, the chlorine atoms, the free radicals that get made, they always get reproduced in this mechanism, which is why they are acting as catalysts and why they can be so destructive, because since they keep getting reformed, they can keep on breaking down more and more ozone. So this final page really sums up what you would be required to know for the IB exam. Just to finish it off, I told you that ozone is seasonal. So this page of the packet goes into more detail about how that works. But I sort of briefly summarized it before. You could take a read through. The other thing I wanted to point out is that one good thing about the ozone hole, this is one of the few environmental problems that humans have gotten together on, and they realized it was an issue, and it's actually getting better. So the ozone hole is shrinking. While it remains a seasonal effect, how bad it is getting, it's not as bad as it was before, and each year it's shrinking. And so it's projected that eventually, right, you can see it kind of shrinking in these images, eventually there won't be a hole in the ozone layer. But even though these CFCs have been banned from production in developed countries since 1995, and now they shouldn't be used anymore around the world, it's still having a lingering effect because it takes so long for the CFCs to get out of the atmosphere that even if we're not pumping any new ones into the atmosphere, there's still enough in the atmosphere that ozone still gets broken down every polar winter and every polar spring. So it's going to take till around 2050, it's projected, before we have an ozone hole that's sort of no longer in existence. But it is one example where we've made some laws and policies that have improved what we've done to the environment. So this page, if I can remind you, this page right here, ozone, what do we need to know, sort of summarizes what you need to know about ozone. For kinetics, the primary focus is on the mechanisms and the role of the chlorine atoms as the radicals.